Welcome, this is question number 3 for AQA AS Physics. This is obviously Unit 1, question number 3. Okay, so there's no real kind of diagrams to draw for this first bit in question. There it is. Okay, so we're given a little paragraph at the start talking about when a clean metal surface in a vacuum is I don't know what that word is, irradiated. It shows how late it is for me. With ultraviolet light of a certain frequency, electrons are emitted from the metal. Explain why the kinetic energy of the electrons has a maximum value. Well, for this, obviously, the equation you need to think about the kinetic energy equation for electrons. Now, there are two ways of answering this question, sort of. Okay? What's that kinetic energy of electrons? That's kinetic energy. Sorry. Equals HF minus the work function. Okay, now we're told it's of certain frequencies. So obviously it's going to be a very strict frequency. So therefore the energy of the photon depends on the frequency. We know that. Okay, well, because obviously H is Planck's constant. Now that means the energy, obviously the energy depends on the frequency. Even if it's certain frequencies, depends on the frequency. So in other words, if it's a certain frequency, the energy is going to be the same. So what energy does is when these instant photons reach the surface of the metal here, kind of draw some crude electrons here. Okay, so anyway, what I'm trying to show here is there's these photons that are hitting the surface of the metal, and obviously these, the first set of electrons, they don't have to do any work to get to the surface of the metal. All the energy they absorb goes straight into them being emitted. Okay, in other words, the energy that they all receive exactly the same energy. So the ones that are lower down in this order receive exactly the same energy as the electrons right at the surface of the metal. But the electrons at the surface of the metal only have a very, very small amount of energy to get to the top, because essentially they're already there. So really, when we're looking at this, the electrons that are at the surface of this metal, all they have to do is overcome the work function, and then any energy left over is given to the kinetic energy. Okay, we assume it's 100% efficient kind of thing. Okay, but the electrons lower down in the metal still have to put a bit of work in to get to the surface of the metal. Then they have to overcome the work function, and then any energy that they have remaining on top of that is kept as kinetic energy. Okay, so in other words, they lose a bit more energy than the ones at the surface of the metal. So as they all receive the same energy, but the electrons further down in the surface of the metal have to put a bit more energy in to get out, they don't have as great kinetic energy. In other words, the ones, it says, explain why the kinetic energy of the emitted electrons has a maximum value. Well, you talk about the fact that energy, they all absorb the same energy, okay, but the electrons up to a maximum value, okay. So you talk about the electrons lower down have to do work to get to the surface of the metal, and then they have to overcome the work function, and then any energy is their kinetic energy, okay. But the electrons at the surface of the metal, okay, don't have to do any work to get to the surface of the metal because they're already there, but they have to overcome the work function, and then any energy excess on top of that is transferred as kinetic energy. Okay, so in other words, they lose less energy getting to the surface because they're already there. So what you would say is electrons near the surface of the metal don't have to do any work to get to the surface, so therefore all their energy is transferred to overcome the work function, and then it's kept as kinetic energy. Okay, whereas the ones lower down, because they have to do work to get to the surface of the metal, they don't end up having as much kinetic energy. So it's up to a maximum value where the emitted electrons with the maximum kinetic energy are the ones that are on the surface of the metal. Okay, so that's why it goes up to a maximum value. but you need to say somewhere in your answer that they all absorb the same energy, because they're all absorbing the same photons and certain frequencies. Okay, so they're all absorbing photons with the same energy, so they all gain the same energy. Just some of them have to use some more of it to get out of the metal because they're lower down. Okay, so hopefully that's quite self-explanatory. 3A part 2, explain with reference to the work function why, if the frequency of the radiation is below a certain value, the electrons are not emitted. What I said, they need to this all comes from this equation here, so what we're going to call this is E equals HF, but when we do F, we call that F naught. That is something called kind of the critical frequency. In other words, it's the minimum frequency required to emit an electron from the surface of the metal. Because, as we see here, for an electron to gain kinetic energy, the kinetic energy is equal to the energy of the photon take away the work function. But if the work function is greater than the energy of the photon, then it almost has minus kinetic energy. That doesn't make any sense. What we're trying to say here is the electrons absorb the photons with the energy equal to HF. Okay, and if therefore, as we said, the energy of a photon depends on a frequency because H is Planck's constant. Okay, so if it's below a certain frequency, okay, then the energy therefore must be below a certain value as well. And if that energy is below a certain value, then the energy of the photon, because we show all the energy of the photon is given to the electron, then the electron does not have enough energy to overcome the work function. So therefore, below a certain value, the electrons don't have enough energy to overcome the work function, so therefore no electrons are emitted. Okay, so that's 3A part 2. Now I couldn't be bothered all writing all that down, it's a simple answer. Okay, 3 part 2, kind of just a knowledge thing. It's a state a unit for work function, and it's just a case of either writing joules or EV. You could accept either. Okay, I'm just going to put joules because it is easier. Okay. So this next little bit of the question is just kind of it's kind of a logic-based question, really. So 3B part 1, well, it is quite a simple calculation, really. So in 3B, we are told that the light energy is instant on each square millimetre of the surface at a rate 3 times 10 to the 10 joules per second. In other words, the energy that is hitting each square millimetre of this metal per second is 3 times 10 to the minus 10 joules. Okay, so every second, each square millimetre, so 1 millimetre by 1 millimetre, is receiving 3 times 10 to the minus 10 joules every second. Okay, and we're told that the frequency of this light is 1.5 times 10 to 15 hertz. Calculate the energy of an instant photon. So we don't need to take into account the rate that it's hitting the surface. It's not asking about that. It just says calculate the energy of the instant photon. Well, quite clearly, we know that E is equal to HF. However, I would also state what you're told in the question. Now, I know it's not obvious straight away that you shouldn't use the square millimetre, but because obviously we wrote E equals HF, the only other bit of information we need in this question is a frequency. 1.5 times 10 to the 15 hertz. Now, you might want to write down what H is as well. But that's totally up to you. So 6.63 times 10 to the minus 34 joules per second. Okay, so it's just a case of subbing your numbers into your formula. So E equals HF, and that is equal to 6.63 times 10 to the minus 34, and that's times the frequency, which is this 1.5 times 10 to the 15 hertz, and then it's just a case now of subbing it into your calculator and getting an answer. Okay, which you get I got 9.945 times 10 to the minus 19 joules, but you just put the answer to 9.9 times 10 to the minus 19 joules. Okay. So that's 3B part 1. 3B part 2 kind of goes on in a similar vein. However, it says calculate the number of photons instant per second on each square millimetre of the metal surface. And you go, what the hell does that mean? Well, just kind of take a step back, because it's not an equation that we know, it's just really kind of using the logic. So it told us that each square millimetre receives each square millimetre receives 3.0 times 10 to the minus 10 joules per second. Okay, so that's the energy received. So that's the total number of. So that's the total energy of all the photons on a square millimetre of this metal per second. Okay, and we're asked to calculate the number of photons instant per second. So that's the total energy they bring. Okay, so that's kind of all the energy. That's the energy of a photon times the number of photons. Okay, so you can think of it like that. So basically, on each square millimetre, that is the total number of photons times the energy of each photon. However, because this energy comes from the light, which we know has a frequency of 1.5 times 10 to the 15 hertz, okay, we've worked out the energy of one of them photons, okay, which is this 9.9 times 10 to the minus 19 joules, okay. And if what this essentially is saying is this 3 times 10 to the minus 10 comes from the number of photons, whatever that is, times the energy of each photon. So to work out the total number of photons, because that's what it's asking, we need to divide it by the energy of each photon. So they cancel out and we get the total number of photons. Okay, and we know the energy of each photon is what we've worked out in part 1, which is this 9.9 times 10 to the minus 19 joules. So in essence, what we've got to do, because this multiplication on top is just this answer, okay, so we just divide this 3 times 10 to the minus 10 by 9.9 times 10 to the minus 19 joules. Now, if you'd have gone, if you'd have done it the other way around, had done the division the other way around for some reason, you would have obviously got an answer that's 0.02 or whatever. You don't have 0.02 of a photon, okay? Anyway, so it's just a case of doing that division and subbing it in your calculator. Now, the answer on the mark scheme is a different one than I've got, which used the same, exactly the same calculation, so I'm just going to double check. Now, what I personally would recommend for this is whatever answer you got for B part 1, okay, save that as your answer, so when your calculator's memory, save that as your as the answer, okay, and then just simply hit the answer button in there. So just copy it in terms of just hit answer and sub it in, okay, and then divide that by 3 times 10 to the 10, okay, so whatever answer said you got for that. So let me just have a go and double check, because I do have an answer, but as I said, in the mark scheme it's got it slightly differently, and it might just be because that I've not typed it in right. Okay. Sorry, second. Yep. I just didn't type it in my calculator correctly. Anyway, that's the right answer, and when you do that division, you get 3 times 10 to the 8 photons. Okay, and that is your answer. Right. Okay, so it's a very, very simple division. And then the next part, 3C, okay, which is the last part of question 3, says, in practice, the time delay calculated in part C does not occur. Okay? Oh, sorry. I've got to do 3C part 1. Where the hell am I going? Okay, sorry. Well, I'm kind of giving away what the next little bit of the question was asking. Okay, so anyway, that's 3B part 2. I thought, I was getting ahead of myself. I thought, yes, I've finished question 3, and I looked and I hadn't. Okay, so anyway, the next little part, 3C, says, in the wave theory of model of light, electrons on the surface of a metal absorb energy from a small area of the surface. The light striking the surface delivers energy to this small area of 3 times 10 to the minus 22 joules per second. The minimum energy required to liberate an electron, okay, is 6.8 times 10 to the minus 19 joules. Calculate the minimum time it would take for an electron to absorb this amount of energy. Now, this is kind of a little bit weird, because you go, what the hell does it mean? Well, as with all of these questions, the thing to do at the start is write down all the information that you get given. So I'll just give you a second if you want to have a go at just copying any of the information down on there that you haven't yet already, because I'm just going to kind of rub off the bits of information at the top that aren't really that relevant. Okay? I'm going to rub all this up. So as I said, you can just nip back and copy that down if you need to. But I don't want a bit of room on the board for this. Okay, so as I said, if you're not 100% sure on what you do on a question, which I can see this question being a bit, what the hell is it? Just write down all the information you've got and try and make sense of it, rather than just trying to panic, okay? So, the light striking the surface delivers energy at a rate of 3 times 10 to the minus 22 joules per second, okay? So the energy per second, so kind of similar to the one that we've done before in 3B, but we've not been told an area. But it doesn't matter, we're just told it hits the area, but we're not told what size this area is. It doesn't really matter, okay? So the energy received per second is equal to 3 times 10 to the minus 22 joules per second. Okay, so that's the first bit of information we've been given. Okay, and we're told that the minimum energy required to liberate this electron is 6.8 times 10 to the minus 19 joules. Okay, so that's a minimum energy required to liberate an electron from the surface. Now, you could go, well that's the minimum, that's the energy received per second. So in other words, it's the energy of the photons received per second. So it's, as E equals HF, you could go, it's the HF per second. But, and you go, well we'll sub that into some equation that we've got, such as the kinetic energy one, okay, which is equal to HF minus the work function. And you could go, well, we could also say this 6.8 times 10 to the minus 19 joules, but it's the minimum energy required to liberate an electron from the surface. Okay, so that's E equals HF, and that's where the F is 0. In other words, the minimum energy required to liberate an electron from the surface. And you could try and sub into some kind of equation. Now, I'm not saying that's wrong at all. Probably is, but I didn't do that route, so I don't really know. But it's one of them questions you just have to stop and think about logically. We don't really have an equation that will help us understand this, okay? Well, as I said, the only ones we have are the kinetic energy equation and obviously the energy of a photon equation, which is obviously given to the electron to help it liberate from the surface. What I'm trying to say is it's just a case of using a bit of logic. Sounds crazy, but bear with me, okay? So, just to recap, the energy received per second is this 3 times 10 to the minus 22 joules per second. But the energy required to move each electron from the surface is 6.8 times 10 to the minus 19 joules. And it's asking, calculate the minimum time it would take to take an electron, so that's a single electron, to absorb this amount of energy. In other words, it's asking what's the minimum time for this electron to have enough energy to literally just overcome the work function. So we know obviously that's equal to the work function as well. Okay, that's what it's just saying. It could have said the work function, instead of saying the minimum energy required to liberate an electron from the surface of this metal, it could have just easily said the work function. That is the work function. So if this is confusing you, you could go, that's the work function. But the reason they didn't do that is because they thought, well, if they said that was the work function, people will try and use the kinetic energy equation or some other variant of that, and we're not going to in this equation, in this question even. Okay? Now, basically, we need a time element in here, because we need to work out how long it's going to take. Now, if every single second the electron is receiving 3 times 10 to the minus 22 joules. So every second it's receiving that, it keeps gaining it and gaining it and gaining it. And we need to know how many of these 3 times 10 to the minus 22 joules are needed. Because then you can work out, well, if that's the energy added every second, okay, how many of them do we need? In other words, how many more seconds do we need to reach this magic 6.8 times 10 to the minus 19 joules? So therefore we've got enough energy to liberate this electron. Okay, so hopefully that makes sense. So again, it's just a division thing. So we know every second that is receiving 3 times 10 to the minus 22. So we need to know how many of them fit into this 6.8 times 10 to the minus 19. In other words, we do 6.8 times 10 to the minus 19 joules over this 3 times 10 to the minus 22 joules per second. And you can quite clearly see. Now, I tried to explain it simply from the method of logic. If that didn't work for you, then look at it this way. What we want is an answer where we've got units in seconds. Okay? And it says joules per second. Okay? In other words, s to the minus 1. And you should know from your basic indice knowledge in maths that x to the minus 1, I know that says s to the minus 1 and that's seconds, but remember this x, we'll use x so it's just a variable, okay? X to the minus 1 is the same as 1 over x, so this s to the minus 1 is the same as 1 over s, okay? Hopefully it's starting to make sense. So if it isn't, don't worry. What it's trying to say here, basically, we want an answer in terms of seconds. So the joules, each equation's got a joule, so we need to cancel them out. And the only way we cancel them out is by taking a joule away from each other. Now, we're not taking the answers away from each other. This in terms of the indices, so we need to divide them is what I'm trying to say. So you can see, these joules will cancel. And because the s is on the bottom, when we move it to the top, we change the power. In other words, this s will now become positive. So this will give us an answer which is in terms of seconds. Will cancel and the s is on the bottom, which goes to the top, okay? So that's obviously going to turn it positive, okay? So you could have just done this question by just looking at the units and saying we need an answer that's in terms of seconds. One answer is in joules per second, and the other part of the question, information, is given in joules. So we need to cancel the joules out and we need to bring the seconds to the top. And the way we do that is by dividing the joules by the joules per second, which will give us seconds, okay? So we divide the 6.8, sorry, we divide the, put the 3 times 10 to the minus 22 on the bottom, and we put the 6.8 times 10 to the minus 19 on the top. And that should be doubly obvious, because if you did it the other way round, well, we're dividing a smaller number by a bigger number, and that would result in an answer less than 1, and that wouldn't make sense logically. Because what we've got here is a smaller number that it's receiving per second. So if you think about it logically, if someone gave you, if you needed £7,000, okay, and someone was giving you £100 a second, okay, I know this is in the context of energy and that's in the context of money, but if someone was giving you £100 every second, you wouldn't need 0.1 of a second to get enough money to buy whatever it is you need to buy. That's very crap analogy, to be honest, but the principle stands that obviously we need an answer that's bigger than 1 for this, okay, and it wouldn't, anyway, so it's just simply subbing them numbers. I've tried to give a best explanation I can as to why that division takes place. Okay, but if you didn't get it, I don't really care, because it's not my job. Anyway, so you get an answer of 2.3 times 10 to the 3 seconds. Okay, so hopefully that's cleared things up. Now we can go into that question I was trying to go on to before I realised I had that question to answer. It says 3C part 2. In practice, the time delay calculated in the first part does not occur. Explain how this experimental evidence was used to develop the particle theory and model for the behaviour of light. Well, it's all about one-on-one collisions. Now, I'll read off the official box here. It says, light travels as particles or photons, so therefore it has a particle-like nature. And obviously particles transfer their energy, okay? And that's essentially what's happening here. Sorry. Let's see. Basically, you need one of these. You need to say that the light travels as particles or photons, okay? And the other part mark is saying there's a one-to-one interaction. Okay, so they travel as particles and then they collide with an electron, implying a particle interaction. So therefore, we can apply it as particles. That's all you need to say. Okay, so sorry about that. It wasn't the most exciting video, but and it's probably quite long as well. But as I said, I was just trying to explain because it was kind of weird. It doesn't explain it. Obviously, it never does on the mark schemes because why the examiners need to waste their life helping out when they're doing past papers? Clearly not. They didn't think of that. But when I come to power, I'm going to make AQA have to put a reason in their mark schemes why they put an answer. But seeing as that's not going to happen today, we're just going to have to live with my crap explanation. Okay, so thanks for watching. If you do have any questions, and I presume you will do, over this division, because that wasn't the best explanation, I'll try and give another one, obviously in the comments, but might not be the best one, because I think that's as good as I can give it, so... stuff if it's not good enough for you, I don't really care anymore. I've had a lot of that lately, to be honest. I don't really care. Good. I mean, I'll probably be redoing this year anyway at college, so I'll have another go at this next year. Okay, so thanks for watching, and we'll see you next video.